All right, let's move on to the next chapter, Electrophilic Aromatic Substitution. This is chapter 18 in the book. What's going to happen here is we're going to take benzene rings. Note, I just put one hydrogen on here. If this was truly benzene, there would be 5 more hydrogens, one on each carbon. We're going to add an electrophile, and we're going to substitute off this hydrogen and put the electrophile in its place. So these are substitution reactions, not addition reactions, like we talked about in the last chapter. Benzene rings hate to do addition. They want to do substitution reactions to keep the aromaticity. Because, as we have said many times, aromaticity means stability. Okay, here are the examples we're going to look at in this chapter. If we take X2, where X is chlorine or bromine, so Br2, Cl2, and we add FeX3. So note, if you're using Cl2, you would add FeCl3. If you're putting on Br2, we would add in FeBr3. We do this reaction, we'll substitute off the hydrogen and put one halogen on there, either the chlorine or the bromine, depending on what our X2 and FeX3 are. We can make nitrobenzene by adding nitric acid and sulfuric acid. That's a nasty combination, but it'll work. Yeah, we put a nitro group on the benzene. Wouldn't it be fun if we were to do a lab that did this? Heck, it'd be fun to do a lab if we do a lab with this. Wouldn't it be fun doing these labs? I think so. Take a benzene ring, put on SO3 and H2SO4. You'll make a benzene sulfonic acid. You'll add this SO3H sulfonyl group to it. Check this out. Benzene ring RCl, where R is just normal carbons, alkane type carbons, CH3, CH2, CH3. With the catalyst AlCl3, aluminum trichloride, you will get a benzene ring with that R group on there. This is a Friedel-Crafts alkylation, when R is just an alkyl group. Friedel and Crafts also found that if you used an acyl group, you put in a double bond here between your alkane type part and your halogen. This is RC double bond OCl. This is an acyl chloride, also called an acid chloride. If you use an acyl chloride with AlCl3, you get Friedel-Crafts acylation. You'll put double bond R on there. And the general mechanism of these reactions is like this. You start with the very stable aromatic ring. You have to get a nice electrophile, and you need a double bond of the benzene ring, or some pi electrons of the benzene ring is a much better way to say it. Some pi electrons of the benzene ring to attack this electrophile. Now, this is going to make this beast right here. It's going to get rid of the aromaticity. Because it gets rid of aromaticity, the product is less stable than our reactant, so this is going to be a slow step. The activation energy is going to be high because of the lack of stability of the product compared to this reactant. However, note these are allylic carbocations, so we do have resonance forms, 3 resonance forms, to disperse that positive charge over the ring and to delocalize these electrons over the ring. So while, yes, the product with its 3 resonance forms is much less stable than our original aromatic ring, it still can happen because there is still some stability here due to the resonance. But then once we have this allylic carbocation, if we have an appropriate base, it will take this hydrogen, the carbon-hydrogen bond will break, and those 2 electrons will form our double bond. We regain our aromaticity, but now we have our electrophile on there, and our hydrogen went with the base. Okay, so the first mechanism we're going to look at is halogenation. Let's look at the halogenation mechanism, this top reaction here. So, It's a little messy here. This is Cl2 right here. Cl bonded to Cl, all the electrons in here. We have our catalyst, FeCl3. Turns out a lone pair of one of the chlorines will attack this iron because we know that these types of transition metal complexes are Lewis acids, electron pair acceptors. So this chlorine has an electron pair, so the Lewis base attacks that Lewis acid right here to make this Lewis acid base adduct, where this chlorine is now bonded to the iron. And when we do that, when we do formal charges, we see this chlorine now has a positive formal charge, and this iron has a negative formal charge. Well, does chlorine like having a positive formal charge? Not really. And it turns out that this is unstable enough, but stable enough to form, but unstable enough as an electrophile that a double bond of the pi electrons will attack this outer chlorine to break this piece off. This FeCl3 with an extra chlorine makes it FeCl4 minus, and that generates this allylic carbocation with the one chlorine on here. And then this pair of electrons here of the iron-chlorine bond will break off that iron, and the chlorine will attack this hydrogen. So we get FeCl3. Remember, there's the whole key with a catalyst. One, it speeds up the reaction. It lowers the activation energy. And two, you get the catalyst back. You have to get it back. So our FeCl3 comes back. We have HCl, and we've now substituted this hydrogen for a chlorine. We have our chlorobenzene, and it works the same with bromine. For nitration and sulfonation, let's look at this. I'm not as worried about this mechanism. For nitration sulfonation, the most important thing is you realize what the products are. However, if we're looking at nitration, recall that was concentrated nitric acid mixed with concentrated sulfuric acid. When you mix those two, here's our nitric acid, our sulfuric acid, you make this beast right here, which you essentially protonate the nitric acid, and then water will break off, and we're left with this NO2 plus ion, which is a very nice electrophile. And then we're back up here. This is our electrophile that will get attacked by our benzene ring. A normal benzene ring, pi electrons will attack this nitrogen, and we'll go through the deprotonation process, and you end up with nitrobenzene. SO3 with H2SO4, you protonate this SO3 to make a nice electrophile. The pi electrons of benzene ring will attack that electrophile. That's the thing about these mechanisms. When we look at our general mechanism that we had right here, the deal is you just got to make this electrophile, make this electrophile such that the benzene ring will attack it. Once the electrophile is made, benzene ring can attack it, get the resonance forms, get the deprotonation back to aromaticity. So the only difference in these mechanisms is generating the electrophile. Once the electrophile is on there, it's the same mechanism for all of these reactions. So here is the bromination or chlorination electrophile. Here is the nitration electrophile. Here's the sulfonation electrophile. Let's look a little more at Friedel-Crafts because more fun stuff happens here. I call it fun. You're going to call it a headache because it's more stuff you have to memorize. All right, Friedel-Crafts, let's look at alkylation and acylation. Is very similar. If you have a benzene ring and you react it with CH3, CH2Cl with AlCl3, you will just put the R group, CH3, CH2, on the benzene ring. So benzene ring with ethyl chloride with AlCl3 makes ethyl benzene. Benzene ring with acetyl chloride and AlCl3 makes it, this is actually called acetophenone. Acid group phenone here makes this compound. Simply, you just put the carbonyl CH3 on the benzene ring. And the way this mechanism works, it's a little bit different between primary and secondary or tertiary alkyl chlorides. If you have this primary alkyl chloride, just as we saw with our halogenation, lone pair on the chlorine attacks the Lewis acid AlCl3 to make this adduct, and that's our electrophile. And then it turns out the benzene ring will attack this carbon to kick off this. We'll get our deprotonation, everything is fine. With secondary and tertiary alkyl halides, say you had this tert-butyl chloride with AlCl3, just as before, the lone pair on the chlorine will attack the aluminum, the Lewis acid, nice Lewis acid-base reaction here, to generate what looks like a very similar electrophile that we had up here. Carbon bonded to chlorine bonded to aluminum, carbon bonded to chlorine bonded to aluminum, positive charge aluminum, positive charge chlorine, negative charge aluminum. But here, at this point, this carbon-chlorine bond is just going to break spontaneously. Here, the benzene ring, the pi electrons of the benzene ring had to come in and attack this carbon to break this off. With primary, with secondary and tertiary, this bond just breaks off on its own to generate this carbocation and our AlCl4. And why does it occur this way? Your brain should remember everything about organic 1 and realize, this is a tertiary carbocation. If this bond here were to break, that would generate a primary carbocation, which is too unstable. Primary carbocation is very unstable, so they don't want to exist. So this bond will not just break because it's makes too unstable carbocation. Here, though, when this bond just breaks, it generates a tertiary carbocation, and the tertiary carbocation, while unstable, is still stable enough to exist. So then once we have our tertiary carbocation, our benzene ring, this is a horrible drawing of the benzene ring here. Let's just cross that out. Don't put this with those two on there at the same time. When you're drawing benzenes, you're either drawing it like this, or you can draw it as one of its resonance forms, like this with the double bond. Never do that. That's just wrong. All right. Anyhow, pi electrons will attack the carbocation, and then we regenerate our catalyst, HCl, and we've got that tert-butyl group on there. Acylation, very similar. The chlorine of the acyl group attacks the Lewis acid catalyst. The carbonyl chlorine bond breaks to make this electrophile, which is resonance stabilized. And then the pi electrons of the benzene ring attack that electrophile. Okay. Now, all seems good in the world, except we've got 3 things we kind of need to worry about. All right. When dealing with Friedel-Crafts reaction, we're going to have some worries. First thing, vinyl halides and aryl halides don't make stable carbocations. They don't do Friedel-Crafts reactions. This chlorine, if it attacked AlCl3, it's not stable enough to do that. Therefore, it doesn't exist for any length of time. So yeah, these guys won't do that. If your chlorine is bonded to a carbon that's already double bonded or is part of a benzene ring, you can't get Friedel-Crafts acylations or alkylations this way. Note that any reagent pairs that form carbocations can be used. Recall in the past we were forming carbocations. For example, if you have a carbon-carbon double bond, you have an alkene, and you react with H2SO4, then that gives this carbocation, right? Now, before we would have some water in there, and this was acid catalyzed hydration of an alkene to form an alcohol. But if you don't add water, you keep water out of the situation, and you have this carbocation, and instead there's benzene in here, you can actually have, well, we've got a carbocation, good electrophile. Pi electrons in the benzene ring will attack that carbocation, and you can put that six-membered ring, the cyclohexane, on the benzene ring. Note, so if you generated our carbocation this way, you put water in there, you'd have just gotten the alcohol. But you put benzene in, note, benzene will not react with cyclohexene. Benzene doesn't react with H2SO4. So just put H2SO4, alkene, and a benzene ring, stir them together. The H2SO4 will make the carbocation, benzene ring will attack the carbocation, and you can put whatever group was on that alkene onto the benzene ring. All right. Note, this was acid-catalyzed hydration of an alkene to make an alcohol. We also did acid-catalyzed dehydration of an alcohol to make an alkene, and that went through a carbocation, or went through the carbocation. Recall, if you have an alcohol and H2SO4, that we protonate that alcohol, and then as long as we've got a secondary or tertiary carbon bonded to the oxygen, water will leave to generate this carbocation. As long as there's benzene in there, benzene is around in there, then the pi electrons on the benzene will attack that carbocation. And so you will not get the alkene if there's benzene in there. Last semester we didn't have benzene in there, so we got the alkene. Now if you throw benzene in at the start of the reaction, you will get this product as well. And here we are again, any acid-catalyzed alkene normally would make an alcohol. Acid-catalyzed hydration of an alkene would make an alcohol. But you have H2SO4 in there, you make this the secondary carbocation, you can add an isopropyl group onto that benzene ring. Okay. But the best part, in my view, probably one of the worst part in your view, is when you have carbocations. Recall, we always have to worry about carbocation rearrangements. Well, that's especially true when we're dealing with Friedel-Crafts alkylations, because if you have a benzene ring with CH3, CH2, CH2Cl with AlCl3, normally we would expect the product of this reaction, well, this is RCl, AlCl3, wouldn't we expect the product to be benzene ring with a CH2, CH2, CH3 on it? Wouldn't we expect just now a normal propyl group on a benzene ring? We would, but that's not what we get. We get an isopropyl group on the benzene ring. Even though this chlorine is on the end carbon, so we'd expect this end carbon to attach to the benzene ring, it doesn't. This middle carbon does. Why is that? Because, as it turns out, when we look at the mechanism here, as this chlorine attacks this aluminum, it makes this beast right here. And normally we said that this carbon-chlorine bond will not break because it would make a primary carbocation. But note, if the bond does break to make a primary carbocation, we know that's very unstable, and we can get a 1,2 hydride shift. We can get a rearrangement, carbocation rearrangement here, where one of these hydrogens moves over to this carbon here to generate our secondary carbocation, which is more stable and can exist, and therefore the benzene ring will attack this secondary carbocation. And that's a problem. You can't stop it. If you have CH3, CH2, CH2Cl, and you put this in here, you will get this, a little bit of primary carbocation will get made. We'll switch to secondary carbocation through rearrangement, and you will get this. And this is all equilibrium, so once this rearranges to secondary, more of this will convert to primary carbocation, which will go to secondary, and boom, this is all you get. You can't stop it. You only get this isopropyl benzene. Question. In our previous example, what we were looking at before, why didn't we worry about this? Well, we didn't worry about this because in the previous examples, when we used the primary carbocation with Friedel-Crafts, it was CH3, CH2. There was no rearrangement possible here. because if this bond were to break and we had a primary carbocation, if a hydrogen were to shift over, we still would have a primary carbocation. So you don't have to worry about it here. Which means if you want to put a methyl or an ethyl group on a benzene ring, Friedel-Crafts will do it very nicely. But what if you actually wanted to put a propyl or a butyl group? You want to put a normal, an N-propyl, N-butyl. You want to put a straight chain of carbons on a benzene ring. Friedel-Crafts alkylation is not the way to do it. So how do you do it? Well, we'll cover that in the next video.